All right. Hey everyone, welcome back to my stream. Today we'll be continuing with the Learning DSA series and we are on stream 5. So, yeah, let's get started. So, yesterday we kind of went ahead and spent quite a lot of time looking through the N Queen's problem. The main thing that I wanted to understand was how come discarding column plus distance and column minus distance works for the diagonal. With the help of ChatGPT, we were able to kind of prove algebraically why this works. Although it's still not, it's something which is still not intuitive for me. But hey, if it works, it works. So yeah. Now, I'm not going to waste more time on increase and I'm going to just move forward. We'll probably come across some problem which requires this concept again and then we look at it. So I've created two files as such, nqueens.py and nqueensmysolution.py. I'm just going to go ahead and, well, my solution is not complete because I have to go ahead and you know what? I think what I'm gonna do is I'm gonna delete my solution and I'm just gonna go ahead and I'm just gonna go ahead and commit this, remove that breakpoint. This is our template. Let's see what I have on my template. I'm just gonna move all these. Well, I don't need this. So I'll just move this to here. I guess I need to commit everything. Bear with me for a second. All right. And let's just commit this backtracking template comma and queen commit, and there you go. Cool. Now let's go back to our course here on backtracking. Was it this? I think the next problem up on list is solving Sudoku. So I also saw computer file video. It was somewhere around here. But well, I mean yesterday it was around here. So let's see if we can find that.
Lynn is a software engineer at Salesforce and an excellent teacher. In this course,
We're now on LeetCode problem 37, the Sudoku solver problem.
All right. Just so I was already kind of aware of the N Queen's problem. I kind of knew what it was. So Sudoku. I haven't actually I think yeah, I don't really know the rules to Sudoku. How to solve it and stuff. I have briefly played it years ago, but yeah, I've forgotten all the rules. So let's just recap on that. How to solve a Sudoku? Oh, WikiHow, right? Sudoku rules are there. Sudoku is played on a 9 by 9 grid of squares. Square grid of 9 large squares. Okay. Yep. 3, 3, 3, right? 3 times 3 is 9. Often called brick. So there's a brick, there's a brick, there's a brick, and so on. Within each of those blocks will be 9 smaller squares. Okay. Some of those squares will be filled with numbers from 1 to 9. Easier puzzles will have more numbers filled in, while more difficult puzzles will have fewer squares filled. The larger squares are often outlined with darker lines, while the smaller squares have a thinner line. Additionally, sometimes the larger square will be colored in a checkboard pattern. All right. Fill the remaining numbers in, making sure they don't repeat. Hmm. Each row, column, and block should contain all of the numbers from 1 to 9. So each row, sorry, this is a row, right? Each row, column, and by block, I assume is it the like the larger square? That means that within a row, column, or block, a number cannot repeat. You always have to figure out where each number goes to complete the puzzle. For example, if a block, large square, okay, already has the number 2 in it, it can't include another 2 anywhere in the square. Similarly, if a column already has a 3, it can't have another 3 even if it's a different block. Okay, it's better to use a pencil. Okay, yeah. Using the scanning strategy. And Sudoku solve. Let's see. Wait, what? They're not sudo. Sudoku solve. I want to solve a Sudoku, not. All right. Mm-hmm. Let's fill this with. I know Sudoku comes with numbers pre-filled here, but I just wanna check whether I understood the rules correctly. Then I guess this can have 7, 8, 9 now. Oops. So 7, 8, 9. This can have 1, 2, 3, and this could have solved Sudoku. Why is there a video here? Oh, does this hmm. I wanna solve Sudoku, not okay, there we go. Select the cell, then tap a number to fill in the cell. Okay. This can have 1 in it. Okay. Okay, I know 3 can't be put in here, but I'm still gonna go ahead. Yeah, it doesn't. Tells me I can't do that. 5. Oh, okay. Um. Ooh. Okay. Then. So that's the thing. Want a easier one? Okay. It's okay. This is the easiest one, I guess. Okay. Let's see. Yeah. 1. You can have 3 in here. You can have 4. 4 in here. You can have. You can't have 5. You can have 6. You can have. Wait, what? Why can't I have 7 in here? It show me the. Huh. I'll just pull up a YouTube video real quick and just check if you understood the rules right. Solve a Sudoku puzzle.
Puzzle game that can be either satisfyingly simple or deceptively difficult. You will need a Sudoku puzzle, a puzzle. Cells where an individual number goes are called squares. Squares are then sectioned off in groups of 9 to create boxes. A Sudoku puzzle has a total of 81 squares and 9 boxes. They create a 3-box by 3-box grid. Many Sudoku puzzles have dark lines separating them. To solve a Sudoku puzzle, each row of 9 squares must contain the numbers 1 through 9. Each column must also contain the numbers 1 through 9, and each box must contain the numbers 1 through 9. No row, column, or box may repeat any number. Step 3. Start with an easy puzzle and work your way up to successively more difficult puzzles. Many squares will already be filled in, no matter the puzzle level. Based on those filled-in squares, using logic and the process of elimination, begin deducing which numbers fit in the empty squares. Any puzzle that has one single solution will have at least 17 squares already filled in.
Any puzzle with a single solution? Oh, alright.
Step 4. Use cross-hatching, the process of figuring out where a number fits by eliminating possibilities based on numbers in the other squares in the same row, column, and box. For example, if the top middle box contains no number 8 and the other boxes along the top row of the Sudoku board contain 8s in the first and second rows, process of elimination dictates the 8 in the upper middle box must be in the third row. Step 5. Once you've solved one square by cross-hatching, use the technique to fill in as many squares in that single box as you can. Step 6. Once you have exhausted one box, either by filling it in completely or running out of discoverable solutions, continue by doing simple cross. Likely there is the same column. His name was invented in the US in 1979 by.
Alright, okay.
which is a hard
Let's go
problem.
back.
If you don't already know what a Sudoku puzzle is, you can read the description. So a Sudoku solution must satisfy all the following rules. Each of the digits 1 to 9 must occur exactly once in each row and in each column. Also, in 9 of
I see how backtracking could work here. Right, because what would be, okay, let's just go back to the template here and oh, okay. I was a bit confused because this folder, yeah. Let's go to template. So what would be a valid state for a Sudoku puzzle, right? We just need to check whether the rules match, whether the rules apply, right? And what about get candidates? Yeah, we just need to provide any number which doesn't occur in the same row, column, or in the same box. So that would be all our candidates, and search would remain the same, and then we would solve it. Should I try this out on my own? Let's give it a shot on our own. I got the basic. I mean, the concept of what backtracking is. So let's see if we can solve this on our own. What's it called? Solve Sudoku or yeah. Solve Sudoku.py. Let's also go ahead and copy this template from lead code. I hope my stream is going to YouTube here. Yep, it is. Let's see. Hmm. Determine if it's a valid Sudoku. Let's see if we can do this. I mean, it's the solution is already given, right? Or not? Okay. Oh, okay. I see. Sometimes it's represented by a dot. So, yeah, output is false. Except with the 5 in the top left corner being modified to 8. 5 in the top left corner. Top left, okay, okay. There's no 5 in the top left. Oh, okay, okay. Let's look at the first part. I think I understand. So this is a valid Sudoku board, yes, but this isn't because 8 appears here, 8 appears here, and your logic is just, gone. Yeah, you know what? I would probably go ahead and create like how I have a repo for Codewars. I'll create one for lead code or something, but for the time being, let's just go ahead and create a lead code folder. Let's call this valid sudoku.py. I think this is gonna be my first lead code problem, which I'm gonna at least try to solve on stream. So let's just remove this error here. So from typing import list. I guess it's not the first one, since technically I did try out the npins problem on stream, but that was not on my own, so I don't. I just consider it as learning, not solving on my own. Right. So we have a board here. This is what a board would look like. It would be an array of arrays. Each array would contain a number in string format or a dot representing an empty space. So what are the rules to Sudoku, right? We need to check if a number first repeats in the same row. Like we can check the same for each and every row out here. Same can be done for each and every column. The box one is a bit more trickier. So we need to check how we can solve that. So let's see. I don't know, can you use maybe using something like NumPy would have been easier for this, but try to solve it just using normal Python logic. And this is something which is, I believe, is also needed for the problem that we're trying to learn, solve Sudoku. So all right, let's think here. I'm gonna go ahead and just copy that board over here so I'm just gonna talk freely here, let my thoughts flow in a way. So if we iterate through each array, we can check whether there are any duplicates in the array, right? Which is not empty, which is not a dot, by the way. We could do that. Something like, but how do we check horizontally? Not horizontally, right? Vertically. Like, how do we check each column? We could have two for loops. For I in range 9. For well, let's just move ij to make more sense. For I guess for row in range 9, for column in range 9. Okay, now what would we do with two for loops here? How do we check whether each column has the correct number or not? If we could make separate arrays for each, separate arrays for each row is pretty simple and straightforward. If we can also make a separate array for each column, right? And if we can make a separate array for each, I believe it's called a brick or the larger square. Um, can yeah, I can select like this, can't I? For each 3 by 3 square, I can construct a individual array for each of these combinations. I can use some logic to I can remove all the arrays and I can check if the length of the set is equal to the length of the array with the dots removed, of course, because they don't count. So maybe something like possible combinations. This will contain each row, column. Where it's called a break, I'm gonna call that break as an array to validate. I guess each row is pretty straightforward. We can just do possible combinations dot append. We can take in the I don't want this board to go ahead. I mean, I'll just ignore the I believe it's called the Linda or something. This under error over here. So we'll append board what the entire row, right? That's pretty straightforward. So we'll append this, and so on, right? Now the main question is, how do we append each column? So yes, we can have column combinations to be let's assign it to a dictionary. Well, actually, you know what? Let's assign it to there was a method in dict called two keys or something. Not two keys. To dict in Python, something like that. Um, list to dictionary Python. There was a fancy way of doing this. I can't find it. Okay, we'll just use I forgot the name. What was it called? You know, these one-liners, I for I in range. Comprehensions? Dictionary comprehensions? Is that what was it called? List yeah, it's called a comprehension. So let's create a dictionary comprehension which says something like this. Column will be assigned to a list for column in range 9, and for column in range 9 we can take in column combinations. We can take in that column and then we can append. Actually, you know what, we need the row, don't we? Oh wait, we can't call it the row. Let's call it the row array. We can append the row array, yes, but here we'll be appending the row array column, right? So we get the each value as such and we assign it to column combination, right? So far it's logical and makes sense. Now what do we do for each brick? That's the main question now. We could, so if we were to label this by indexes, let's check here. I'm gonna just start a comment here. Actually, you know what? I need a bit of space here. So, what? I guess I can just that should work, right? Yeah, we'll just keep it as it is for the time being. Just trying to explain, anyways. So, this would be 0, oops, 1. Why does it keep on entering a new line when I click the right arrow? It just goes into a new line. 3, 4, 5, 6, 7, 8. Remember, these are indexes, not the actual row and column as such. We have 0, we have 1, 2, 3, 4, 4, 5, 6, 7, 8. Again, not too many spaces. Alrighty. So we could go ahead and do some kind of logic here, can't we? If we divide these bricks into, let's call this brick 1, and this brick 2. From 3 to 5, it's brick 2. 6 to 8, it's brick 3. It's basically a sort of a combination that we have, right? How do we put this in a dictionary? What would do we use? We can have the same concept as column combinations, but something like brick combinations. But the main thing is, what do we use for for a key here, as a key here? Um, or you know what? If we just have the column combinations and if we have the row combinations, can we get the brick? I think we can, because it's just a matter of who knows slicing better, right? Yeah. Okay, so this should give us all the list of all possible columns and rows, right? How about we, after this, we can have a separate loop for calculating brick um, combinations. Before this, I guess we can just validate row and columns real quick and return false. Hash validating rows and columns. And then for calculating the brick combinations, we can just slice. Now, how do we slice this? So, what would be the list of possible indexes? Let's write that down. For the first brick, it would look something like we would need row till 3. Then we would need row till 3. Well, we would need the first 3 rows in a way, right? We so these indexes, so I'm guessing, how about we do something like this? We can check whether the row index plus 1 is a multiple of 3. Until we reach a multiple of 3, we can just append this, because we're already getting a row here, right? And this takes care of the column. Let that be there for the time being. I guess what we could do is we could say hash calculating brick combinations. Let's see here. This is row 1, 2, 3. These 3 need to be split into 3 again. If we floor divide this by 3, what will we get? We'll get 0. We'll get 1. We'll get 2. But that's for each row, right? Huh. I guess we could have a brick combination which could have something like 0, 1, 2, and we'll reassign this 0, 1, 2 whenever the thing comes up. What I mean by 0, 1, 2 is this would, if I were only to consider the rows from 0, 1, 0 to 2, this would be the first brick, this would be the second brick, and the next would be the third brick. Hmm. So what would be our base condition? If the row floor divided by 3, we could have something called brick number. Brick number will be set to this initially, and each iteration will check if the brick number is still has that value. If it doesn't have that value, then we'll reassign brick number to be that value. Basically, this tells us when hash it this tells us when we are entering a new row set. Okay, we've taken care of that, and brick combination will reassign it to be this. Oh, actually, you know what? we can just, instead of having 0, 1, 2, we can have 3, 6, 9 here. And after doing this, we could do possible combinations. We could extend brick combination dot values, right? We can extend the possible values here. And then we can reassign this to be empty again because we're starting off new again, aren't we? Else, what are we gonna do? We're gonna slice the list. So for brick index in brick combination, we could take in whatever brick index is there, and we can, I believe it should be extend, not ex, yeah, it should be extend. We should extend the row. For brick index, and we can enumerate. I don't. We can enumerate. I think we can enumerate a dictionary, can't we? We'll see, and we can start at. No, we can start at 0. This would basically be the start index. So we'll start from the start index times 3, right? That way. Oh, you know what? We don't need to do. We don't need to make this more complicated. We just need brick index, and the start would basically be from brick index minus 3 all the way till brick index. So that would be 0 to 3, 3 to 6, 6 to 9. You get the point. Yeah, this should work. I think okay, let's see if we get all the possible combinations here as a result. And after this is over, column combinations and possible combinations, we can just merge them together. So yeah, what about it? Let's test this out. Yeah, let's just adjust this. And I guess after the entire thing is over, we could extend possible combinations with the column combinations. Just add a print statement for our debugger. All right, let's see if our logic works. So create an instance of solution, and we can call sol dot is valid sudoku, and we can pass in, you know, let's consider this to be the board here. So board equals this, and let's pass in board here, and we board, and let's see if this works. Possible combinations and column combinations. Let's check what column combinations is. Yep. As expected, it's array having keys from 0 to 8. Each value would be an empty list. Brick combination is going to be this. Brick number has, oh, but it's not associated with the value. So just set that to 0 for the time being. For row in range 9, let's see if we got the correct row array. We have. That's a possible combination. We're gonna append it. Calculating brick combination. That's, it is the first brick set brick number, so it's not gonna execute. Now let's see if this worked as I predicted. It should give me 53 dot as the array here, and it doesn't. Okay, end object is, oh, this should be row array. Right, let's just see if this works. Should, but the combination, okay, it's working. Let's just retry again. Come there. Now for column in range 9, let's see. We will get 5 and we'll get, let's come back here. Let's go to the next row. And let's see what we have in column common. Yay, there we go. We have 5, 3, dot, dot, 7, dot, value at the point. Yeah, this should work, I believe. Let's try to come in here. Let's see what we have so far. Inside possible combination, we have 4 rows. Yeah, because we're on the 4th. Okay, that makes sense. And what about inside brick combination? Let's see. We have 5, 3, dot, 6, dot, 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 9, 8. Okay, and we should have, let's just try to not pretty print, I guess, but format this in such a way so that we can make more sense out of it. Next, we should have dot 7 dot 195, 3 dots in a row. Then we should have 3 dots in a row, 3 dots in a row, dot 6 dot. All right, it's working. It's working. And we're gonna extend this, and we're gonna reassign brick combination. Would you look at that? That's working all right. Do we even need to have, okay, let's just have possible combinations for the time being. I'm gonna exit out and see what I get as a result. Is this the end of the, oh, it is the end. I'm gonna remove this and see. We should have what, 24. Okay, this is, there's something weird happened here. Oh, was it because we try, yeah, this need to be, we need to extend dot values here. That's the reason. Let's try this first. Let's reassign possible combinations to be, I believe, the first 14 values. Okay, and let's do this. Okay, there we go. Should we have 24 values? Is that right? So we should have 9 rows. We should have 9 columns. That's 18 already. And we should have 6 larger squares. 4, 5, 6. No, we should have 9 squares, right? Should have 1, 2, 3, 4, 5. Okay. Do we have dot 6 dot anywhere? I think the last brick combination was not assigned. look at brick combinations again. Yeah, the last one was not assigned because it doesn't go through the loop, right? So let's just extend this once more. Or I guess we can just have a or statement here. Or if the row equals say, if it's the last row, well I guess no, because yeah, that's not gonna work well. Not gonna work well. Um hmm. Yeah, let's just copy this over. Not this over. Just copy this over and have it here. Let's just rerun this. We should have, I believe, 27. Yeah, there we go. So we have all possible rows, columns, and breaks now. Now to validate this symbol, we can just let's write another function here. Define validate combination, or I guess we can just do is valid. We can take a combination, which is obviously a list of string, returns a boolean value. Let's pass in self here, and we return whether the length of the combination is equal to the length of set of combination, which it wouldn't be because it has, you know, all the dots in it. So we can combination is value for value in combination if value not equal. I guess we can just do value dot s digit. That works too. And then we just check this. So whether this is a possible combination or not, we can know by doing any, not any, all, right? So what does all do? For those who are not aware, all returns true if all the elements in the array are truthy, right? If at least one of them is false, say a falsy value, sorry, I add falsy value like false, it returns false. So you could have something like this, right? And remember, an empty string is falsy in Python. This would return false. Any does the opposite. If at least one, or not the opposite, I guess, but if at least one of the element inside an array is truthy, it returns true, else it returns false. So with that logic in mind, Sudoku is only valid when all the combinations like do not have values repeating in it, right? So it would be what do we have to return? Do we have to use any or do we have to use all? Yeah, we'll just, if we just return all of, like if returning all of is self dot is valid combination for combination in combinations and possible combinations. This should tell us whether the board is a valid Sudoku or not. Because if at least one of them is false, then it's not a valid Sudoku, is it? And here it's a valid Sudoku, and yeah, it is. I mean, I agree with that. What about this? This should not be a valid Sudoku. I think we can just collect this as the output, and we can just print the output. False. Okay, it's working well so far. Let's change this back to 5. So we've tested a row here. How about we test a column now? This should return false. I just have to return false, and let's turn it back to true again. And let's test a break. How do we test a break now? Huh. Need to find a larger break here. I think I found one. If I put 7 in here, it doesn't appear in this row. I mean, it doesn't appear in this column. Doesn't repeat in this column. Doesn't repeat in this row. But this is not valid because it repeats in the break over here. This should return false. What happened? Character not allowed. Huh. Not sure what happened there, but anyhow, we got the result as false, which is, it's right. I think, yeah, this is it. This is our solution. Let's just copy this over into LeetCode and yeah, see what it has to say. Moment of truth. All right, okay. And if we submit this, yes, there we go. We solved our first ever LeetCode problem on stream. Geez, this is the first time for me because I didn't expect. I thought there might be some error of sorts. At least syntax error. Well, not a syntax error since we tested it, but man, I'm just so happy right now. There we go. That worked. Although, okay, LeetCode has this thing where it shows me how efficient your solution is. It says in memory, in space complexity, I'll be beating the other solutions 31% of the time. And then time complexity, I'll be beating it 5% of the time. So let's see what would be a better solution. I guess, I mean, we can already optimize this, can't we? Because we don't need to get every possible combination. Each and every moment that we get an array, we can just run is valid and return the thing, right? So actually, why don't we do that? So I guess for brick combinations and column combinations, it has to be done at last, but for the row we could do it at first. For the timing, I believe is fine. Let's just run with it. But again, I'm just so happy we are able to solve one, and that too on our own, right? Amazing. Anyway, the reason that I covered this is so that I can, but like this solution is gonna act as our no, this logic that we have built out here will be used for the solve Sudoku problem there. I guess we can use this to validate the state. I'm just looking to see if I can find other more efficient. Do I have to click on this? Oh, all right. Um, valid Sudoku. Subscribe. Oh, okay. Um, okay. This beats 96% of other solutions in runtime. Let's see what they're doing. It initializes an empty list called res, which will be used to store all the valid elements in the board. Right? It loops through each cell in the board using two nested for loops. For each cell, it retrieves the value of the element in that cell and stores it in a variable called element. If the element is not a dot, which means it's a valid number, right? The method adds three tuples to the res list. What's a three tuple? The first tuple contains the row index and the element itself. The second tuple contains the element itself and the column index. The third tuple contains the float division of the row index, the float division of the column index, and the element itself. This tuple represents the 3 by 3 subgrid that the current cell belongs to. Length of res is equal to the length of the set of res. So it followed that logic, and oh, I see what. Huh. All right. I see what how that works because you will have. Let's just see if I can. There we go. So the way this pretty much works is that rather than having three separate arrays, three separate, rather than having multiple dictionaries and whatnot, it just has a single list called res, and it would basically increment 0, 5, 0 being the row index, 0, 3, 0, 7. So in that case, if we have 0, 7 appearing here again, guess what? That's not a valid solution. You can just return it, right? You can return it on the spot. Well, not well, they haven't returned it on the spot, but you get what I mean, right? Like at the end, they have this check. If they see 2 0 7s in that, obviously this will convert to false, and then we would know it's not a valid Sudoku solution. Same goes for the column logic too. What about the brick logic? Aha, I see. So to make sure that it's the same brick, what they've done is they've assigned a number. So this first brick would be basically 0 0, right? I believe 0. Okay, this let me just move this forward so it makes sense. This would be so this brick would be 0 0. This brick would be 1 1. This brick would be 2. Sorry, not 2 2. Oh, my bad. The first number is the row, right? So this would be 0 0. But here it would be 0 1. Here it would be 0 2. Aha. That's pretty clever. All right. Let's just go ahead and um. Oh yeah, like God was. Let me just go ahead and I'll probably move this to a separate repo later on. But let's just write fast here, and let's just write. Um, let's just provide the link to that problem, and I believe that should be the link. And let's see. Um, we'll find a way to better organize this later on. Let's just create a new file called palette sudoku best solution.py. Yeah, we need a better way to organize that for sure. But yeah, I'll just copy this for the time being. Let's also give this, I believe, is the upward equivalent in lead code, maybe. So let's just copy that, paste that in there. Let's also paste in the link there. Hash beats 9. What was it again? What was the stat? 96.78%. All right, let's go back. All right, so far so good. We've been able to solve well, one lead code problem, but let's go back to the main. Okay, if I reload the page, would the status change to? Oh, yeah, it's marked as solved now. Let's go to Sudoku solver now, and let's see here. Let's see if we can use our current knowledge and solve this. Um, solve sudoku.py. Have we copied over the? We have not. We just copy this, remove this. Do not return anything. Modify board in place instead. Okay, I just have to modify this. All right. Okay. I don't have to return anything. Just have to modify this. Okay. Before I begin, let me just get. Yeah, let me just take a quick break here, and I'll be right back. Alrighty, I'm back. Let's get back to it. So, let's go ahead and try to attempt solve Sudoku on our own. So, let's just read the problem statement first. Write a program to solve a Sudoku puzzle by filling the empty cells. A Sudoku solution must satisfy all of the following rules. Now we know the rules pretty well that we have solved the valid Sudoku problem. The dot character indicates empty cells. Okay. Um, the input board is shown above, and the only valid solution is shown below. Uh-huh. Board dot length 9. Okay, this is just constraint. It is guaranteed that the input board has only one solution. All right, we just have to return once we. But I guess yeah, we don't have to return as such. I guess, but anyhow, I guess we have to return to end the program, but we don't have to return the board as such. Is what the thing is saying. First and foremost, let's get rid of the lending problem here from typing import list. Then let's check here. So this is from our template, right? Does the okay? It doesn't have anything. It just has board in it. Let's pass in self to everything. Um, this needs self. This needs self, self, self. I think that should get rid of. Yeah, it got rid of all the syntax errors there. Not syntax errors. All the problems there, I guess. Okay. Let's see. We need to think this as a backtrack. Think of this as a backtracking problem. So first and foremost, when would a state be a valid state? Well, that comes from a valid Sudoku problem here, right? But I mean, a valid state in this context is not whether these, solution. It basically means if the entire thing is solved, right? Because this logic would go in the search part or something. So I think is valid state should return. The state would be basically a board, right? It would be what? It would be a. Actually, you know what should state be? State doesn't necessarily have to be the board. Hmm. Uh huh. What can I use to store? Okay, what do I exactly want state to be here? Something to keep track of the solution. Mhm. All right, how do we do this? Let's think. Does it make sense for the state to be a board? Um, no, I think state should be a single array. How about, yeah, how about we take the tuple logic from the best solution in the valid Sudoku and use that to advantage here. So we could indicate this by saying 005 can be 013, 024, 036, and so on. Hmm. Would that work though? Hmm. But okay, let's just assume that it would work. If it does, what would be the problems that we would face? So what are we gonna try out here? Let's just go back. Okay, I'm not gonna copy this again. And can I paste it like this? Alright, let's think here. So if I were to represent this as a state, my thought is can be represented like this. We have 005, we have 013, we have 024. You get the point. It would basically be row, row index, column index, and then the value. If we are able to, if we make this the state, then I mean converting this into this is, yeah, it's gonna be simple. It's just gonna be, we're gonna iterate through this and we can do this easily, yes. Now what would a valid state be in this case? I guess it would be, if the logic ensures that no number is duplicated and all that stuff, a valid state is gonna just return whether the length of that state, but then what about dots? Let's just assume we're not gonna have, if we don't have dots in here, I think I can still do this. Let's just say the valid state is gonna be whether the length of the state is equal to 81. 80. Where did I get 81 from? It's basically 9 times 9, the area of the Sudoku board, I guess. Right. Now, how would, okay, if it's a self dot valid state, we append state dot copy and then hash convert to bot. This is something we have to do. Then let me just adjust my camera here. Um, what would get candidates to? So what are the possible candidates? Candidates are gonna be basically the a set of numbers till, well, starting from 1 all the way till 9, right? That's what candidates is gonna be. Now that we have the state with us, and remember, state looks something like this. How do we eliminate stuff? Let's think of this as an empty board. Let's just say the Sudoku board is empty. It's all covered by dots, or our state looks like this. In that case, I can place a number anywhere I want to, right? I can, you know, like the possible candidate would be any number in any number from 1 to 9, right? Inclusive. Um, so I guess what I have to check is, I'm kind of thinking whether we made the right decision of this being the state. Because we have to. How do we make sense of this? How do we get the? How do we discard candidates based on the state? Okay, let's just say we get this. We get the list of candidates. Then I guess I need to know the position I'm trying to place the thing at, right? Yeah, I might be given a board like this. So I can't. Oh, I guess I'll have to just get the first board, which first state element which has a dot in it. So does that mean we would be? As we need to change state, right? Len of, if state has dot in it, then it would be I for I in state. If I negative 1 dot is digit. Let state be a list of tuple which has string in it. Is this how you do this? And string. Maybe I need to define it as a. Also, I'm thinking on whether a tuple would make sense here, because I can't update the tuple. I can only remove it. We need to think that over, but let it be a tuple for the time being. Is now what we'll do is um hmm, Let's think here. Yeah, it doesn't see what the. I think let's go ahead and look at the solution. There's something I'm missing, and I think I'll be just wasting time here trying to figure out a solution on my own. So let's take a look and see. Anyway, we got so far. I mean, we did solve the valid Sudoku problem. So let's see what the solution, what this would look like in terms of backtracking.
The 3x3 sub-boxes of the grid. And LeetCode used the dot character to indicate empty cells. So for example here, LeetCode wants us to write a program that fills out this Sudoku puzzle in a valid way. The board is represented as a 2D array of strings. Some might be numbers, some are empty cells, and LeetCode wants us to solve the problem and modify the board in place. The constraints are that because it's a Sudoku problem, the shape is 9 by 9, and if you find copy-paste All right, so again, we adopt the solve function like this. Because it asks us not to return anything and just modify the board in place, I think we'll just need to do solve.search board. And then we can get rid of the solve function. I'm going to have to define some constants here. So the shape is 9 by 9. The grid length is 3 by 3 if we are trying to validate the sub-boxes.
Mm-hmm.
And empty is represented as this dot here. And all the digit strings are like follows. So string number for number in range 1, shape plus 1. So this gives us the string from 1 to 9. And I'm going to wrap it in a set because the order is not important. And I know I'm going to need this when I'm traversing the grid.
All right. Okay.
Great. So let's start by writing the isValidState function. So it should take self and the board and check if the board is a valid solution. So let's validate all the rows first. For row, I'm going to just define some helper function later down. So let's do first self get rows, which returns each row of the board one by one. If my row is equivalent to all the digits, then it's a valid row. Otherwise, it's an invalid row and the entire board is not valid. If not, set row is equal to self.digits, return false. Validate. Similarly, we validate the columns. Get cause. Return false. And lastly, we validate the sub-boxes. For grid in self.getGrid board. And if all the rows are validated, all the columns are validated, and all the grids are validated without causing this false return early, we return true. meaning that the board is now a valid solution. Now let's write get candidates. So self, board, a row, and a column. I'm using the row and the column because for a cell, I want to know which row and which column it is on to determine what digits have already been used and what are left for us to use as a next state. So used digits is a set of digits, and I'm going to remove digits used by the same row. So used digits dot update self dot get kth row. This is another helper function that I will define later down. Remove digits used by the same column. So used digits dot update self dot get kth column board and the column. And remove digits used by the 3x3 subbox.
Get kth grid
Grid it is on.
row column. Okay.
Board row call. And lastly, because we might have already used the empty string here when we are doing the updates, we subtract those from our used digits.
So discard.
Self.empty is the constant that we define for the empty string, and candidates are just whatever that's left for us to use, so the unused ones.
I like how sets are used quite a lot in DSA problems, whereas I mean I worked in quite a lot of production systems, and sets aren't used that much in them, but they're like used everywhere in DSA.
And that concludes our get candidate function. Now we are moving on to do search. Because we only have one single solution, we don't need the list of solutions here. So self and board. We have is valid state, so if self dot is valid state board, we return true. Found solution. Otherwise, we find the next empty spot and take a guess. So for row, index row, we enumerate board. For column index, the actual element in enumerate row. If the element is the empty string, so self dot empty. For if this is empty, find candidates to construct the next string, next state. For candidate is self dot get candidates board. Now that we have the row index and column index, we pass those in. We modify the board in place as the problem instructed us to do so. Candidate. Remember that candidate is just one of the digit string. And because here our search returns a boolean, if one of the search actually finishes, that means that the board has been modified in place and our problem is solved. So is solved is now equal to self.search board. And just to add some comment here, we recurse on the modified board. If it's solved, then we just return true, meaning that the entire search has completed. Otherwise, we undo the wrong guess and start anew. So we make this entry back into the empty string that it was.
And the for loop runs again
And
until we
have exhausted all the
get a
candidates.
candidate which works.
But none solves the problem. We return false because this is an invalid succession of searches. And if no empty spot in the first place, then we just return true. And we can get rid of this board. And if no empty spot, we return false because this is an invalid succession of searches. And if no empty spot
So we go back to the previous thing that we modified and try another option there, and yeah.
In the first place,
Okay.
then we just return true. And we can get rid of this boilerplate code from our template. Now the structure is pretty much clear, and all I need to do is to fill in those helper functions. Helper functions for retrieving rows, columns, and grids. So here are my helper functions for retrieving rows, columns, and grids. This is pretty straightforward because our board is just a 2D array, and to retrieve the kth row, kth column, or grid at a certain row and column indices, we are basically just doing some really smart indices, and sometimes relying on the power of ether tools. I will post my complete code on my GitHub linked to in the description, so you can digest those helper functions on your own. Now let's run the code and see what we get. Great, our output is accepted. Let's submit and test it against all the test cases. Awesome, with this template, we solved 2 legal hard problems.
All right.
To recap, a backtracking problem is all about finding valid states. To solve for a valid state, we identify candidates that satisfy the problem constraint and use them to build upon our current state. Once a modified state is valid, we add it as a final solution. Now that we have solved 2 problems hands-on, let's take another look at our template. Recall that we have these 4 functions. IsValidState is a helper function with a Boolean return value that validates whether a given state is a final solution. GetCandidates is another helper function, returning a list of candidates satisfying the problem constraint based on our current state. Search is a recursive function that calls the 2 helper functions, IsValidState and GetCandidates, and recurs on itself. Lastly, solve is the function that a legal problem is asking you to write. It does nothing fancy other than initializing an empty list of solutions and an empty state and calling search on them. For more practice problems on backtracking, go to leetcode.com and in text, search for backtracking. This filters out a list of questions that all shares the backtracking idea. You see we already solved Sudoku Solver and nQueens. If you're looking for a medium hard problem, I recommend the subsets problem. This is about finding all possible subsets or power sets of a given integer array. It is pretty easy to identify a backtracking
Oh, the person I remember that from a math class.
problem when we are asked to find all possible solutions and may return the solution in any order. As you can see in my submission details, I solved the
Oh wait, don't show me. I mean, show me the solution. I'll try to solve it on my own. Yeah, that was a pretty good course. So what I guess I'll do is it's I'm ending the stream now. It's 1 hour 40 minutes since I started it. Today was a productive day though because we solved our first problem again on LeetCode. And for solve Sudoku, I'll just leave it as it is and we'll come back to it. For the time being, let's just get more practice on the on some other backtracking problems. So again, as a reminder, I started this entire thing, or as a reference, I've been using the developer roadmap provided on roadmap.sh for DSA, and I've been going through problem solving techniques. And there's an article by Geek for Geeks, which I believe also had there we go, standard problems. So yeah, let's go ahead and solve some, right? And yeah, as always, let's keep on learning. And I guess that's what I'll be doing in my next stream. Try to see if I can solve, now that I understand what exactly the concept of backtracking is, and since these all share some similarity, all these problems, right? They can be solved in that solved using that problem solving technique. Yeah, let's try our hand in solving them. Okay, great. With that, I'll be ending the stream now, and I'll see you on the next one. Take care.